Now let us discuss the naming of aromatic aldehydes and ketones. Now what do we mean by aromatic aldehydes and ketones? Suppose the aldehyde group or the ketone group is attached to a ring. Then how do you go about naming these compounds, right? So let us take a few examples. You know, this is the benzene ring, and suppose you have an aldehyde group attached to this benzene ring. Then how do you name this compound? So this is simply called as benzaldehyde because it is obtained from the parent hydrocarbon. There is benzene, so benzaldehyde is attached. So benzaldehyde is the name given to this particular compound. Now in the IUPAC system, you have the name of the hydrocarbon followed by carbaldehyde. So this you can say is the common name of this particular compound. And in IUPAC system, you can call this particular compound as, although very often it is called as benzaldehyde in both the systems, the correct IUPAC name for this particular compound would be benzene carbaldehyde. So you take the full name of the hydrocarbon, the parent hydrocarbon, and attach the suffix carbaldehyde. So it is benzene carbaldehyde. Let us take another example. What is this? This ring is definitely different from the above ring. The above hydrocarbon to which the aldehyde group was attached was benzene. Now we are attaching the aldehyde group to a saturated system, that is cyclohexane. So what would be the name of this particular compound in the common system and in the IUPAC system? Let us see. Now this is the parent hydrocarbon here is cyclohexane. So since the aldehyde group is attached to cyclohexane, this is called as cyclohexaldehyde. Cyclohexaldehyde. So what is the IUPAC name of this compound? Let us see. The parent alkane is cyclohexane, and you write the name, the complete name of the hydrocarbon first. So you have cyclohexane, and you have to add the suffix, that is carbaldehyde. So this is cyclohexane carbaldehyde. Now what happens if there are substituents attached to the ring? How do you name those substituents in the common system and the IUPAC system? Let us see. So suppose you have the benzene ring, you have the aldehyde group, that is CHO, and you have a substituent, say Br here, and you have CH3 here. How do you name this particular compound? Now as usual, we will name the hydrocarbon, the parent hydrocarbon, that is benzene. And where are the substituents present? In the common system, the position of the substituents is indicated by the symbols alpha, beta and gamma. Now what is this alpha? Alpha is the carbon directly attached to the aldehyde group or the carbonyl group. So this is our aldehyde group. The carbon directly attached to the aldehyde group is this. So you call this carbon as the alpha carbon. The next carbon is called the beta carbon and followed by the gamma carbon. So you have to indicate the position of the substituents using these symbols alpha, beta, gamma, whatever applies. Now in our particular example, the bromine is present at the beta position. So it is beta bromo, and methyl, there is a methyl group attached at the gamma position, and alphabetical order you will name. So you have beta bromo, gamma methyl. So that indicates the position of the substituents, and this is benzene, so it is benzaldehyde, right? So the name of this compound becomes beta bromo. Why is it beta bromo? As we have seen, the carbon directly attached to the aldehyde group is the alpha carbon. Since it is attached at the next position, it becomes the beta position. So beta bromo. Then you have gamma methyl, benzaldehyde. Benzaldehyde, basically the compound here is a benzene ring with a CHO attached. The common name of that particular compound is benzaldehyde. So that name remains the same. You simply indicate the position of the substituents using the symbols alpha, beta, gamma and so on. So the name of this particular compound is beta bromo gamma methyl benzaldehyde. This would be the common name of this compound. Now how do you think we are going to name in the IUPAC system? The only difference here is you are going to, instead of using the symbols alpha, beta, gamma, in this particular system we use the numbers 1, 2, 3 and so on. And the carbon directly attached to the aldehyde group, that ring position is taken as 1. So you have to take the least numbering possible as dictated by the rules of IUPAC system. So the IUPAC name of this particular compound, I am sure you can guess, is, what would it be? It is benzene. You can call this as benzaldehyde even in the IUPAC system. But instead of alpha, beta, gamma, we are going to put the numbers as 1, 2, 3. So there is a bromine at the second position and a methyl group at the third position. So 2 bromo 3 methyl benzaldehyde, you can call it as 2 bromo 3 methyl benzaldehyde. Or more correctly, you can use this name carbaldehyde too. So it is benzene carbaldehyde. Benzaldehyde is also called as benzene carbaldehyde. So the same name can also be written as 2 bromo 3 methyl. There is no difference in this. This indicates the position of the substituents, and then you can write this as benzene carbaldehyde. This also is a correct name for that particular compound, benzene carbaldehyde. So this is how you name aldehydes which contain ring systems involved in them. So whether the ring system is saturated or unsaturated, you take into account the name of that saturated ring system when you name these compounds. Let us see how compounds that are ketones, the ketone group, if it is attached to a ring system, how do we go about naming such compounds? For example, you can have a benzene ring and C double bond O and CH3. As you can see, there is a carbonyl group here, there is a methyl group and a phenyl group attached here. C6H5 group is called as a phenyl group. Now how do you name these? So ketones containing the benzene ring as one of the substituents are known as phenones. So what are phenones? Phenones are ketones having one of the alkyl groups as the phenyl group. We know the phenyl group is the C6H5 group, that is the benzene ring. So any ketone containing the benzene ring as one of the substituents would be called as a phenone, and the other part of the name, the prefix to that, would be related to this particular group, that is the acyl group. Now CH3CO is called as acetyl group, isn't it? So because the acyl group has the name acetyl in this particular compound, this is called as acetophenone. Now let us see, suppose both the substituents attached to the carbonyl group are benzene rings, then how do you name this compound? Now this is called as benzophenone because it is benzoyl group. There is a benzoyl group. So the ending phenone always indicates that one of the alkyl groups in that particular ketone is a benzene ring. So when one of the substituents is a benzene ring, the name always ends with phenone. This is the common system of naming. So this is called benzophenone. This is acetophenone and this is benzophenone. So where are you getting these names aceto and benzo from? They are coming from the acyl group part of it. The acyl group is COR group. So this is obtained from the acetyl group, so acetophenone. This is obtained from the benzoyl group, so it is benzophenone. So phenones are ketones containing one of the alkyl groups attached as the benzene ring. We have already studied the rules for writing the names of aldehydes and ketones in the common system and in the IUPAC system. Now let us test our knowledge, how much we have understood in naming these compounds. So let us do an exercise on this. Let us take the first compound as alpha methyl propionaldehyde. Now from the name itself, can you guess what system of naming is this? Just by looking at the symbol alpha, you will know that it is the common system. So this is a common name of an aldehyde. As you can see in the name, it says aldehyde. So this is a common name for the given aldehyde. Now you are supposed to write the structure corresponding to this name. So how do we go about writing the structure? If you have really understood the rules, you will be able to write the structure for this compound. Now it says alpha methyl propionaldehyde. Prop meaning 3 carbons, isn't it? So propionaldehyde must be an aldehyde containing 3 carbon atoms. So let us add 3 carbon atoms in a straight chain like this, and let one of the carbons be involved in the aldehydic functional group. So this is propionaldehyde, and it says alpha methyl. Alpha methyl means the alpha indicates that it is a carbon atom directly attached to the aldehydic group. So the carbon directly attached to the aldehydic group is this. So since it says alpha methyl, there must be a methyl group attached at this position. So the structure of this compound would be, if we were to satisfy all the valencies of carbon, then this would be the structure of alpha methyl propionaldehyde. So as I told you, alpha indicates that it is the common name or the trivial name of this aldehyde. Prop indicates it has 3 carbons in its structure. So you have written a 3 carbon aldehyde in a straight chain, and the methyl group is present at the alpha position, so it must be present here. So this must be the structure of the given compound. Similarly, let us apply to another compound. Let us try to write the structure of this particular compound. Now from the name itself, you see the number 2 here. 2 indicates, can you tell me whether it is the trivial name or the common name or the IUPAC name? Common names have alpha, beta as the numbering for the positions of substituents, but if there are numbers like 1, 2, 3 and so on, obviously it is the IUPAC system. So this naming is an IUPAC name for this particular aldehyde. As you can see, it says carbaldehyde. So it is the IUPAC name for the aldehyde. Let us try to write the structure of this particular compound. Carbaldehyde simply indicates the presence of the CHO group, that is the aldehyde group. And the parent alkane, as you can see over here, is cyclopentane. Pent meaning 5 carbons, so there must be a cyclic structure with 5 carbons. So we can show the cyclic structure like this. So this is cyclopentane, and carbaldehyde, as I told you, it indicates the presence of the CHO group, that is the aldehyde group. Now it says 2-hydroxy. Now this position where the aldehyde group is attached to the ring, this is said to be the position 1. So we want hydroxy group to be present in the second position. So obviously it must be here. So there must be a hydroxyl group attached at the second position in the cyclopentane ring. So this must be 2-hydroxy cyclopentane carbaldehyde. Similarly, let us try to draw the structure of 3-hydroxybutanal. 3-hydroxybutanal. Butanal. So but meaning 4 carbons. 4 carbons, and one of the carbons must be involved in the aldehydic group. So this must be carbon 1, that always gets the highest preference. So the least number should be given to the aldehydic carbon. So this would be 2, 3 and 4. Now you need a hydroxy group to be present on the third position. So this would be 3-hydroxy butanal, and filling up the hydrogens you would have this to be the structure of 3-hydroxy butanal, right. Now let us take one more example, that is let us try to write the structure of a ketone. Disecondary butyl ketone. So di meaning there are two of these groups. Which groups are present? The secondary butyl group. Now you have to attach two secondary butyl groups on either side of the carbonyl group to get the structure of this ketone. Well, let us see how that is done. CH3. This is the secondary butyl group, right. So this is one, and the carbonyl group C double bond O, and on the other side you have a similar group, that is the secondary butyl group CH3. So this would be the structure of disecondary butyl ketone, right. So this is how we apply the rules that we have learnt for writing the common names and the IUPAC names for the various aldehydes and ketones, right. Now let us go on to the importance of the carbonyl group that is present in both aldehydes as well as ketones. All the properties of aldehydes and ketones are related to this particular group, that is the carbonyl groups. So let us understand the structure of this carbonyl group and how it affects the reactivity of these particular compounds. As we know, the carbonyl group is C double bond O group with 2 free valencies. Now as you know, oxygen is highly electronegative compared to carbon. So this double bond, which is made up of 1 sigma bond and 1 pi bond, the pi electrons, they spend more time on oxygen, making oxygen negative, and the carbon becomes positive. So you can show the resonance over here as C O minus and plus with the 2 valencies. So this resonance in the structure of the carbonyl group results in the polarity of these compounds. So aldehydes and ketones are found to be polar in nature. That means they have a positive pole and a negative pole. The negative pole being the oxygen and the positive pole being the carbon. Now this makes the carbon end of the molecule to be positive. So this is an electrophile. The carbon becomes, this particular spot becomes electrophilic in nature, that is electron loving. Since it is positive, it is electron loving. So you say this is the electrophilic center of the carbonyl compound. As I told you, carbonyl compounds include both aldehydes as well as ketones, because this group is present in both aldehydes and ketones. Obviously, if this is the electrophilic end of the carbonyl group, this is the nucleophilic end. What is the meaning of nucleophilic? Nucleophilic means nucleus loving. We know that nucleus is positive. So the oxygen end being negative, it attracts the nucleophilic end of the reagent. So this is called as a nucleophilic center, and the carbon is called as the electrophilic center. So the oxygen with the negative charge behaves as a Lewis acid, Lewis base. What is a Lewis base? Lewis base is a substance which has excess of electrons in it. So that is why it gets the negative charge, because the pi electrons are delocalized more over the oxygen atom of the carbonyl group. Hence the oxygen end behaves as a Lewis base, whereas the carbon end of the carbonyl group behaves as a Lewis acid. right? So, coming to the structure of this carbonyl group, as you can see, the carbonyl carbon is involved in the formation of a double bond with oxygen. Now, the double bond indicates that this carbon must be sp2 hybridized. And we know the geometry of sp2 hybridization is trigonal planar. That means this carbon is attached to 3 other atoms through 3 sigma bonds and 1 pi bond. Now, these 3 sigma bonds are formed by sp2 orbitals of the carbon are overlapping with the orbitals of the combining atoms. That means the 3 atoms attached to the carbonyl group must be planar, because the geometry is trigonal planar for sp2 hybridization. You would expect that all the 3 atoms to which the carbonyl carbon is attached must lie in the same plane. So, the sigma bonds would lie in the plane of the 3 atoms and the carbon, whereas the pi electron cloud is formed by the overlap of the pure p orbital which didn't take part in the hybridization of sp2 of carbon. So, that pure p orbital of carbon overlaps with the p orbital of oxygen to give you a pi bond. The electron density of the pi bond would be distributed in part of it would be above the plane of these combined atoms and the other half would be below the plane of these atoms. So, you could visualize the pi electron cloud in this manner. So, you would have these bonds are present in a plane, the combined atoms along with carbon would be present in one plane, the pi electron cloud, half of it would be above this plane and half of it would be below this plane. So, this is how you can visualize the structure of the carbonyl group.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.